Hello, this lesson in electronics is about timing and clock circuits. Time is really determined by any regularly repeating event. If you think about it, whether it's the sun that rises each morning and goes down each night, or the positions of the stars and constellations that come back to the same year after year, so we know the length of a year. So in electronics, oscillators are circuits that produce changes in voltage or current at regularly repeating time intervals. For example, an AC wave or a square wave used for digital circuits alternates between a high and a low voltage value. So changing voltage or current can be used to control changes in other circuitry at regular time intervals. So oscillators are used for timing, controlling timing in electronics. And there are many applications that need timing control. For example, just having a delay after a power switch is turned on before something happens can be a useful feature. I think of a car turn signal. You put it on and it blinks every so often. Or windshield wipers, even the delay wipers, that a certain amount of time passes before it wipes again. Alarm clocks, alarms of all kinds, camera shutter speed control, radio frequency control also, and communication protocol timing. A lot of times in communication, what's important is how soon things happen, and so controlling the timing allows communication to be possible. Switching between transmitting and receiving, oven timers, even something as simple as a toaster, to have a timer that goes off at a specific time so you don't burn your toast. And computers, if you think about how much a computer, every operation on a computer depends on a certain timing of the clock in the computer. So many more uses of circuits to control timing. Timing control is so important in electronics. Since timing is done by oscillators, let me list three main types of oscillators. The first are crystal oscillators. Crystals can vibrate or oscillate when a voltage is applied to them. They vibrate or oscillate at a very specific frequency. There are also resonant LC tank circuits. I'll leave that for another topic for another lesson. Third example is RC circuits, or resistance capacitance circuits, and that's what this lesson is going to focus on. To understand that, we need to understand how capacitors work in DC circuits. So I've sketched a very simple DC circuit. All it has is a voltage source and a single capacitor. I've drawn the capacitor with little charges. I'm going to use conventional flow, so we'll think of these charges as positive charges. And these charges are sitting on both capacitor plates. So in this condition, when both the top plate and the bottom plate of the capacitor have the same amount of charge, we call it an uncharged capacitor. As soon as we connect the circuit to the voltage source, current will start to flow. That battery or power supply pushes the current, so the charges start to move onto the plate. They actually move onto the top capacitor plate and drain from the bottom plate back into the source. As the charges build up on the top plate, more and more charges, they're all the same charge, and one of the laws of this universe is that opposite charges attract, but the same charges repel. So as more and more of these charges build up on the top plate, they're all repelling each other. They're also repelling the charges off of the bottom plate, and they're attracted also to the source, and they drain off into the source. Charging slows as the top plate of the capacitor fills up with charge and the bottom plate of the capacitor empties of charge. Now on this diagram it shows no charges, and that doesn't really happen because all atoms have electrons in them, so there's always charge on the plate. But the idea is that the top plate is as full as can be and the bottom plate is as drained as can be. And as the top plate gets full, it pushes back with an equal force as the supply is pushing forward, so at that point current stops. So capacitors don't charge instantly. They can't, because it takes a certain amount of time for charges to move from one place to another. So when a capacitor charges through a resistance, a certain time is required to charge that capacitor. Now it charges up fastest when it's first connected to the voltage source. And as the charge builds up on the capacitor, they repel additional charges being added, causing the charging to slow down. So when the voltage difference between the capacitor plates creates the same voltage as the supply, then charging stops. So if we were to graph the charging of a capacitor over time, this is kind of what it would look like. It starts very fast at first, slows down, and eventually almost stops. It never quite gets to 100% theoretically. Now for discharging, the same kind of concept applies. A capacitor just discharges fastest when it's first connected to a ground or a return. As the charges drain, there are fewer charges that remain on the plates to repel each other, and that causes the discharging to slow until the same charge exists on both capacitor plates, and at that point no voltage difference exists in the capacitor, so discharging stops. So a discharging graph would look like this. Discharges fast at first and slows over time until it almost stops. So here's some formulas. The formula for a charging capacitor. This one is in the special case of charging it from 0 volts. Of course, V represents the voltage at whatever given time. V sub F is the final voltage or the source voltage. It's the voltage that is theoretically attainable. T is the time in seconds, and RC is called the RC time constant, or the Greek letter tau. And that's simply the resistance multiplied by the capacitance. If you have the resistance in ohms and the capacitance in farads, then the time constant will be measured in seconds. And here's the formula for a discharging capacitor, discharging to 0 volts. So V would be the voltage at any given time. VI, V sub I is the initial voltage, or the voltage the capacitor was to begin with. Time is in seconds, and the RC time constant. So is a capacitor ever fully charged up to the supply voltage level? Well, theoretically, it never reaches the supply voltage because charging is exponential. In other words, it charges fast at first and slows down. So for example, the first time you might measure a capacitor, say after 1 second, it could be 63% full. After 2 seconds, 86% full. 3 seconds, 95%, and then 98, then 99, 99.8, 99.9, 99.97, and eventually it just keeps getting closer and closer to 100%. And the same is true for capacitor discharging. For all practical purposes, electronics technicians and engineers consider a capacitor completely fully charged after 5 RC time constants, or 5 taus. So what will happen if we increase the size of the capacitor? If the size of the plates is increased, we change that capacitance. It should take longer for that capacitor to charge. There's more area, more room for charges to fill on that plate. Or what would happen if we increase the resistance in the circuit? We could add a resistor, and what that does is decrease the amount of current flowing, and so it takes longer for charge to build up on the capacitor plates. So in a series RC circuit, it's also called an integrator circuit. It's named an integrator because the math function that approximates the charging curve is an integral. But timing can be controlled by the charging or discharging time of a capacitor, and that timing can be adjusted by changing the capacitance or the resistance or both. I'm going to have my students do a lab exploring RC time constants. In this lab, we connect a digital multimeter to a voltage source in a series circuit with a large resistor. In this case, I've chosen a 1 megohm resistor, and I'm just using a 9-volt battery as the voltage source. And current will flow from the battery through this red lead to the breadboard, through the resistor, through this alligator clip that's connected to my meter. Current will flow through the meter, back out through this green alligator clip, back to the supply, the battery. Now in this circuit, I'm charging a capacitor. As current flows from the battery, through the red lead, through my meter, back from my meter along this green lead to the capacitor, and back out to the battery. This circuit shows discharging the capacitor. And in this video, this shows how to connect the circuit to discharge. Current has charged up this capacitor, and so what I'm going to do is by plugging in this white jumper wire into this row with the capacitor, I'm going to allow the charge to go from one side of the capacitor back through the meter to the other side of the capacitor, and we can read on the meter as the capacitor discharges. And you'll see that as soon as I plug that in, it's reading a negative voltage, which means just the direction of current flow, basically, and that it discharges and reads the voltage of the capacitor while it's discharging. I'm going to have my students record the voltage of the capacitor at set times and also the voltage on a capacitor while discharging, and prepare graphs using Excel, or these graphs compare measured capacitor charging time and discharging time compared to the calculated charging and discharging time using those formulas. So let me give you just a few examples of timing circuits. Don't worry about the rest of this circuit, but what I want to point out is the series RC circuit, the resistor in series with the capacitor. That again is used to set the timing of the circuit. Here's a crystal controlled circuit, but again it has a capacitor C1 in series with R1 to set the time for that circuit. This is a very common circuit in digital circuitry. It's called a multi-vibrator circuit. And again, notice the resistors and capacitors. We've got C1 and C2, and the resistors that work with those capacitors, and changing the value of capacitors or resistors changes the timing for the output of those transistors that can be connected to say an LED to blink a light. In fact, I'm going to have my students build this circuit and do this assignment to explore timing with a multi-vibrator circuit. I want to mention before I end, one of the most popular timing control circuits is a 555 timer IC. Probably the most popular IC that's ever been created. It was invented by a man named Hans Kamenzind in 1972, and more than 1 billion of these 555 ICs are produced every year. They are so useful in all kinds of timing applications, turning lights and sounds on and off, activating servos or motors. They're used in robotics all the time. Almost any application where timing is used. I just want to show you the typical DIP 8 package is a very common packaging type for this. It's a dual inline package with 8 pins, numbered 1 through 8. This diagram shows the insides of a 555 timer. The reason it's called a 555 is that inside there's 3 5k ohm resistors in series. Here's a block diagram showing the functions of each of the sections inside a 555 IC. So for our purposes now, this is more what I wanted to show you is you can ignore all of the circuitry inside the IC and just realize that to control the timing of how often it turns on and off, you can adjust the resistances and the capacitances that attach to the trigger and the discharge. So adjusting R1, R2, and C can control the timing of the 555. It's really an oscillator circuit, but it's also called a multi-vibrator because it vibrates back and forth between high and low voltage states. Capacitor is charged through a resistor, and when the voltage reaches a certain level, it discharges through another resistor. So the timing really depends on the resistor and capacitor values. And that's all I'm going to say about 555s for now. They'll be the subject of another lesson later on. So to summarize, timing in electronics is managed by oscillators. Timing control in electronic circuits can be managed by RC circuits. And an RC circuit controls the timing dependent on the capacitance and resistance values because it takes a certain amount of time for a capacitor to charge or discharge. And that's how it controls how quickly things turn on and off. So thank you. I hope you learned a lot. I hope you enjoyed that, and hopefully it helps you in your pursuit of electronics.